something with the system attaining thermal equilibrium. Like, as far as I understand, even Susskind had proposed this law of black hole complexity. Like, there are black hole microstates. The greater the number of microstates, the greater time a black hole takes to attain all those microstates. As you were saying, the greater the number of n, the greater the complexity. So, and after is it something like after a certain state when it attains all the states, it equilibrates or something?
It thermalizes or something?
Yeah,
it's a relative thermalization. In the context of black hole.
The complexity. The complexity
there are
doesn't.
many complexity. Krylov circuit, and
I think it was circuit.
Yeah.
Krylov
But
is
anyways, complexity is
but there's context in which it is being used to find it. Like Krylov is used for this kind of product that you were saying. That is okay, you can continue.
But the Krylov complexity saturates after a certain time, so I guess
It does saturate.
It does saturate after a certain time.
Right, when you will show the figures, I think it will be clear.
So we can we did the Krylov complexity complications, the calculations of the Lanczos coefficients for state vectors. We can do the same for operators as well, and it will also generate the same Lanczos coefficients, the same amplitudes, and the definition of Krylov complexity will still be the same. Now we can study. We need to study a relation. Is there any correlation between the chaos, quantum chaos, and Krylov complexity? So for that, we'll see how the Lanczos coefficients behave for integrable or chaotic systems. So we'll in particular look at the variance of Lanczos coefficients. So we'll look at the variance of Lanczos coefficients and we'll compare our results with the usual probes of chaos, like the level spacing ratios. Or the Lyapunov experience. A and B. For state vectors, we'll have two Lanczos coefficients, but if you do the algorithm for operators, we'll only get BMs. We will not get AMs. So, in particular, we'll look at a particular example because we need something to So we need to find the Lanczos coefficients and then compare them. So we'll look at the stadium billiards for a geometrical picture in one quadrant. I can write the stadium billiard in the following way. So select triangle up to
Remove which side?
this is a stadium billiard.
But taking cross section? Stadium
yeah.
is like if
Yeah,
the full is
it will group like four quadrants. I'm just taking it in one quadrant. Since I think the reason they are taking it in one quadrant is that if you take all the four quadrants, then you will get degenerate eigenvalues. And if you do the level spacing ratio with degenerate eigenvalues, you will get it will blow up somewhere. If you are calculating the ratio of maximum of 2 divided by minimum of 2, so you will get 0 by 0 there. So I guess that's the reason they are doing it only in this one quadrant. Now the first stadium billiard, A by R or the A by R ratio is equal to 1 for stadium billiard. For a circular billiard, however, A by R ratio is 0. You can just see it geometrically also. If A goes to 0, then you can just see this shrinks here and you get the 1/4 of a circle. So in the entirety of it will make a full circular billiard. Now stadium billiards are chaotic systems, we know that. Circular billiards are integrable systems, we know that as well. Now we'll see how the Lanczos, the variance of the Lanczos coefficients as we move through A equals to A by R from 0 to A by R to 1. We'll see how the Lanczos coefficients behave. Now So for instance, for this stadium billiard, if you write down the Hamiltonian for it, Hamiltonian will be px square plus py square plus b of x alright, b of x is 0 inside the billiard. And infinity outside.
V is variance.
No, V is the potential. I'm writing the Hamiltonian for the stadium billiard. It's
Takes a later.
now for this Hamiltonian we can do like we can find the eigenvalues, we can do the level spacing ratios, and we can plot them for different values of A by R essentially, or the Lyapunov coefficient for different values of A by R. Level spacing ratio we'll talk about, but it's a way to determine like chaosity from integrability.
Are you going to talk about it?
No, actually we talked about it already. I can just write that for any, I said that for integrable systems the level spacing distribution is like Poisson distribution, and for chaotic systems it's a Wigner-Dyson level distribution. So that ratio, the level spacing ratio for integrable systems,
You're saying the level spacing, you're taking in account energy levels, right?
yeah. We talked about like, I thought we talked about like the level
But it
spacing.
was, I think, a short of that.
Okay. This one is so we said that let's say for our Hamiltonian here, if you find the eigenvalues and you do like a level spacing, like you calculate a particular ratio of like let's say the maximum of En plus 1 minus En, comma En minus En minus 1 divided by the minimum of the same thing. These are the eigenvalues. These are the eigenvalues. E0 is the E1 is the first one, E2 is the second one, and so on. So if you find, so if you calculate these ratios R's for all the eigenvalues, you will get like a set of data, like set of R's here, and you can do a probability distribution of those R's. So if that probability distribution looks somewhat like this picture, like this. So your spacing ratio, the P of R, I would say, P of R versus R. Now, if that picture looks somewhat like this, then your system is integrable. So,
The Gaussian question.
no, the Poisson
Poisson.
statistic. So, your distribution will look something like this. And in case if you are dealing with say chaotic systems, your distribution will look something like this. This is called
Wigner-Dyson.
This is called the Wigner-Dyson statistics. The Wigner-Dyson, we say that in chaotic systems we get level repulsion. We say that because you see that the probability that the spacing is really smaller, than zeros are really close together, that's really small in chaotic systems. So we also say that chaotic systems display level repulsion. That's what we mean by that. So we have this probe now, like we have this probe to determine chaos or integrability. We'll take that into account, and we also calculate the variance of the Lanchos coefficient. So we see that
those numbers.
What were the numbers? Just example.
0.386.
So if you so we know we have these probability distributions. Now if you calculate the expectation value of or like if you calculate this integral, right? This integral dr from r to 0 to infinity, and you also normalize it at the same time. Now if you do this for integral, you put the probability distribution like for you will put the Poisson probability distribution here, or you will put the Wigner probability distribution here. You will get this number. So this number is termed as like the average level spacing ratio R, and it has particular values for integrable systems and chaotic systems.
For all, like,
For in general.
general.
Yeah, it's general.
General.
It's a general description because Poisson, all integrable systems will show Poisson level statistics.
And that R is, the number is same for all.
Yeah, average will be the same. If you normalize it in a certain way, it will always be the same. For integrable systems, it will be equal to 0.386 or this is Poisson. This is Wigner-Dyson. Gaussian orthonormal ensemble.
Number is called the level spacing ratio.
Number is called the level spacing ratio, the average level spacing ratio. And so we'll calculate, we'll see how the variance of, we have like the Lanczos coefficients Cn and Vn. We can find the variance of these numbers. It's easy to find the variance of a data set that we have, statistically speaking. So if we plot those variances for this stadium billiard, and we're dealing with the operator complexity. We are doing, let's say, for, you can choose any operator, you can do the complexity for P of x, and we find the Lanczos coefficients for P of x, and we plot them. Plot them with this is level spacing ratio. Now we observe that the variance, like we get a higher variance for the smaller ratio. Like there will be a lot of terms here, similar points, there will be a lot of points here, and for lower variance we get points like here. This sort of a behavior. So this implies that higher the variance of the Lanczos coefficients, we observe that we get a level spacing ratio which is close to the Wigner-Dyson levels. So there's kind of hints.
Roughly looking like that.
Yeah. There will be points there. Yeah. There will be points cluttered here and cluttered here if you do that.
That's like two lobes of that.
There will be a lot of points here, a few scrambled points here, and then a lot of points here. And
That is the interval, the range for R. R is the level spacing ratio.
yeah.
So for 0.3 it will be integrable.
For 0.3 it will be integrable, and for 0.53 in particular it will be chaotic. I'm varying
This is variance for Wigner-Dyson.
I'm varying my like I said, I'm varying my A by R so I can study the transition as well. I'm varying my A by R, I mentioned that. So A by R goes from 1 from 0, 1, 2, 3, 4, 5, 0.0, 0.1, something like that. It goes from 0 to 1 like this. So as I move through, like I calculate for 0.0, 0.1, 0.2, 0.3, I get like a lot of points like this for different values of A by R.
What is the A by R? It's 0.
For circle billiards, it's 0.
So and it's near that point. Okay, then it's integrable. It's near point 3 something.
This
Okay.
region is integrable. So
yeah. So
when I
for circle it's integrable.
Yeah.
It shows that it's integrable.
yeah. And these are chaotic regions.
Billiards and others.
So in this stadium billiard, as we like change the A by R ratio, as we move closer to 0, then you'll see that the points will be coming right here. And as you go through A by R equals to 1, you'll see the points that appear here. So it implies that it kind of hints that the variance of the Lanczos coefficients is small for chaotic systems and it's high for integrable systems. And this can be verified with the Lyapunov coefficients as well. We'll see that the Lyapunov coefficients, they increase, sort of they increase like this. As
You're
you-
talking about the maximum Lyapunov, right?
as you go, yeah, the maximum Lyapunov coefficient for A by R. So as you A by R equals to 0 is a circular billiard, so that is integrable. And as you increase it, it will go to a higher value.
How
And
is
then
the variance of the level spacing ratio related to the entire?
they are correlated. We are arguing that the level spacing ratio and the variance of the Lanczos coefficient, they are correlated. That's what we are arguing here.
By making this comparison, like, because of the sigma square cluttering in that region, it's integrable and near the arbitrary and chaotic. So somehow it should be.
Yeah, that's what we are arguing, that the variance of the Lange's coefficients are correlated with the level spacing ratios. So we are saying that the variance can be studied instead of the level spacing ratios to know the chaos or integrability of the system. That's what we are arguing here.
How is it?
How they are correlated?
How they are correlated. You can think of it. Okay, so we can talk about the one-dimensional chain again. Just series model. Now this variance can be understood in the one-dimensional chain.
Like City is asking how that graph is plotted, lambda a by r. Like how are you plotting it? Like you are slowly changing a by r for different systems. Like for a billiard only.
For a billiard,
going from a circular billiard to this stadium or this billiard. So slowly you are changing a by r, and at that for those a by r's you are making the lambda, basically analyzing the lambda and then making a plot, right?
there will be points here. I'm just like drawing a continuous line, but there will be points.
Plot.
Yeah, so there will be lots of points. I'll just make this. I'm just trying to show that the a by r per equals to 1 is chaotic. That's what I'm showing here. So what was the question? What's the correlation between the two? So our, like I said, that the variance coefficients, they denote the hopping amplitudes on our chain. So sine plus 1, sine minus 1 and so on. So let's just say you have defined some hopping quantities. And let's just say the variance of the BNs are higher in case of our integrable systems. Let's say the variance is higher. That will, so if the variance is higher, the amplitude will not spread out smoothly. So the particle will be localized around the initial position. Right? If the variance is high, behaving erratically. So that will mean the complexity is small. So that would mean the system is integrable. Like I said, the system with higher
variance is high, the particle is localized to a specific state.
Because the variances are high, they're erratic, right? So let's just say like for here it can be -4 or it can be +4. They're not behaving smoothly. So if the variance, that's what a variance means. So they're not, the data set is not behaving like smoothly. The data points are spread out, let's say. They're spread out. And in that case, if you calculate the average position, which are erratic Lange's coefficients, you'll see that the particle just behaves like sits around the mean value or the initial value. And that should imply like if the curiosity is small, then the system is integrable. And if the system is integrable, then like we see that for erratic Lange's coefficient, the variance will be high.
We are saying like for high variance, particles sits around mean position.
Around the originals.
But so you're talking about states, right? Here it's the states of the particle. I mean, state could be anything, right? And here the variance is
For
just
the stadium billiards, we are doing like for an operator, we're not doing for a,
Okay.
we're not doing for a step. We're doing an operator Krylov complexity, not the state Krylov complexity. These are just the, like I'm just noting the amplitudes this way. I'm only arguing that if the variances or if the Lange's, if the hopping parameters are erratic, they are not smooth, so my particle will be localized around like the initial position. But if my variances are small or if the Lange's coefficients are not behaving erratically, my particle will not be at the origin, it will be like at some higher point rather than the origin or zero.
Right.
And higher complexity means a chaotic system, and like I said, chaotic system will have low variance of the Lange's coefficient.
Yeah. But it's like a correlation.
I think there's something more like you were saying, if it has the variance is higher, like higher than
More spread out.
coefficient is
We have more spread out. Data set is spread out.
so okay. So we can also define those variance in these states, like how it's spreading out. Like, but he just said if we take the expectation, it will be near the origin, like the initial, like the sign of. How do we know that?
Well, okay, so I can say that my Lanchos coefficient, like these popping parameters, they tell you to like with what coefficient or with what amplitude you move to the second term,
Yes.
or with what with probability you will go to the previous term. Now, if they are erratic, they are not smooth, so it will not go in one direction. So let's say at one position it tells you to go 4 steps ahead, and when you go to a second point, the Lanchos coefficient is erratic there also. It's not moving smoothly. It tells you to go. The coefficient tells you to go back 4 steps. So you're just moving erratically. On an average, you would stay around your initial or the mean position.
It's like a trend.
But it also works
Like a
the
random
way-
walk.
Random
Like in a random walk, you will just stay around the origin. So if the variance is like the Lanchos coefficients are random or they're erratic, they're not smooth, then you will like stay around the origin. That's what I mean.
You won't be able to cover all the
You are
space.
able to move higher in your chain. Because that's the intuition why they are correlated. And like this is this behavior is called like the long time dynamics because we study it for the entire T range, I guess. But there's also a short, if I plot the complexity. So, with different varying my A of R here.
No, wait. If we're comparing to this, if we are comparing to that the drunk guy problem, we can also say the same thing about if we have like uniform coefficients. But there's still, I mean,
Not uniform, less erratic, I would say.
yeah, erratic, not erratic, it doesn't really matter. Like in those problems, the probability of taking any side is all same, right?
The probability of taking.
Like the guy taking left or right is the same, right? It is.
It is.
It is the same. In that case, the guy just moves around the origin, right? So, but here you are saying that if the probability is almost similar, if it's not erratic,
Then
it's
it's more less pure. It is near
Similar.
because the number of states that it requires are less, so the complexity will be less. Right?
Yeah.
That it is just making an analogy because the more the spreading, you are at the center, you are not going anywhere. So the number of states that you will use to make your Krylov basis will be less, and the complexity will be less. But if the other way around, if it's more like the what you call data set is more low variance, then you will have exact number of that it's going here, it's going here, and you will have more space to cover. Like you are going in more. The more the Krylov basis you are covering, the more the complexity.
Okay.
So we can plot the Krylov complexity now for different AYR values in our stadium here. And we'll notice that for like say AYR equals to 1, which is the chaotic part, it grows exponentially fast, attains a peak and then it saturates like this. For AYR equals to 1, let's say.
Okay, this is the how it's
Goes
this is the behavior of Krylov complexity as you move in time.
Yeah, time dependency of Krylov complexity. And like for different values it will be like this for AYR medium and so on. And for like for our integrable integrable system, AYR equals to 0, we'll see like a linear behavior of Krylov complexity before it saturates. As expected, I guess the Krylov complexity.
This thing or this sudden jump is basically the signature of the system to be more
Chaotic.
complex or chaotic.
You can say that, or you can just say that the complexity increases exponentially.
Okay.
It increases exponentially before it saturates for chaotic systems, and for integrable systems it just grows linearly or let's just say quadratically maybe before it saturates. That's like the early time, like the studying it for a short time to see how the complexity behaves. And for a long time behavior, you can just calculate the variances and see if they are correlated, like how your variances are, how your the variance of Lanczos coefficients are behaving, to know about the chaos of any system. So we can use the Krylov complexity equally the same way as we use the level spacing ratio to determine chaos state. That is the argument.
Okay. Anyone has questions? Questions? Nikesh?
Oh, by the way, the hoping principle, sorry, the hoping mechanism, even in condensed matter, sometimes, no, not sometimes, most of the time it's taken like that, B1 with different coefficients.
Okay, but like what exactly is causing, like if you're mimicking this problem
No,
in terms of
it kind of makes sense, right?
There is no symmetry here. Like I guess that
this is like
there is no symmetry.
transitions.
No, there can be, it can be equal, but you can kind of make sense of it like, it's like transition probability between two states. They can be different.
Yeah, they can. Yeah,
So,
I'm not saying they
yeah,
cannot.
makes
But like,
sense.
it's something, some asymmetry should induce that difference, right? Otherwise, like, what's the reason for it?
Yeah, that is true.
Just asking, like, if we are mimicking it in terms of the popping, what exactly in that framework?
What does
what
A
exactly is causing that
and plus 1, like why are they
different from side?
And so the one thing remaining is I think we need to talk about is that phi n and phi n plus 1, those original differential equations that we need to talk about, and maybe you can go ahead and take just one example and just calculate it all, like how you are making Krylov basis, and from there you are calculating. So just one example, maybe in the next lecture we can talk about it.
Yeah.
Okay, so let's thank the speaker.